Alright everybody, we have one last video about gas laws here. And in this video I would like to talk about something called root mean square velocity of gas particles. And this is something that I would imagine that the vast majority of you have not seen before. And that's fine. We're going to go through some of the principles behind this and then come up with the equation and then actually use the equation to calculate the root mean square velocity of a particular set of gas molecules. So where does this thing come from? Well, it comes from the fact that the ideal gas law that we've seen before, the PV equals nRT formula, this is actually a simplification of what the actual formula is. There are several assumptions that are made in order to simplify this equation about the nature of gas particles and how they interact with each other and how they interact with the walls of a container. And those assumptions are called kinetic molecular theory. You'll see that in this current section of the textbook. And it turns out that in a particular sample of gas, no matter what's in there, particles of different masses all have approximately the same kinetic energy, or the same average kinetic energy at a particular temperature. So if you have hydrogen, nitrogen, carbon dioxide and oxygen all in a particular container, they would all have approximately the same temperature, the same kinetic energy, even though they all have different mass. Now, many of you will have seen this relationship before, that the formula for kinetic energy is half mv squared, where v is the velocity and m is the mass of your particle in kilograms. If that's the case, if these different particles have the same average kinetic energy, and yet they've all got different masses, that must mean they're traveling at different speeds or different velocities. And that gives rise to this thing right here. In a gas at a given temperature, whatever that is, lighter particles travel faster on average than heavier ones. Now that makes sense, as you would expect for anything, really. You would expect lighter things to travel faster than heavier things. So it's exactly true in chemistry as well. But because we're talking about particles of different mass and we're talking about they all have approximately the same average kinetic energy, and we have this dispersion of speeds from fast speeds to slow speeds. In a particular gaseous mixture, what it's useful to talk about is something called, it's some sort of an average velocity of those gas particles. Alright, and that average velocity is something known as the root mean square velocity of that gas. Alright, and that's given the symbol URMS, which is the square root, hence root, 3RT over M. Now we just need to clarify what exactly these things are, because they're a little bit different than we've seen before. T, of course, is temperature in Kelvin. That's not really a surprise. R is the gas constant. However, we're dealing with energy at this point. We haven't dealt with energy before when we've talked about gases. And when we have a particular energy unit, in this case joules, in our value of R, because the units are different, so is the value of R. Alright. It turns out in this case, when we talk about the value of R, when it contains an energy unit, the value changes from what we've seen before to 8.314 joules per mole per Kelvin. Alright. Before it was liter atmospheres per mole per Kelvin. Now it's joules per mole per Kelvin, and because the unit's different, that's why the value is different as well. Notice we still have Kelvin here, so we need our temperature being Kelvin. The M is the molar mass of the species that we're talking about, except it's a special molar mass, special because of its units. Usually we talk of molar mass in grams per mole. In this particular case, it's kilograms per mole, and we're going to see why that is here in just a minute. When we talk about root mean square, we're talking about something units of meters per second, and I'm going to show you when we do a calculation here of how, when we have the molar mass in units of kilograms per mole, we can have all our units here cancel out to give us meters per second. We can't do that if we have grams per mole, so that's why we have to have our molar mass in units of kilograms per mole. But the point is, the formula for this root mean square velocity is shown right here. I'm not concerned that you guys know how to derive it. That's not the point. I want you guys to know how to use it, same as we have always said. So, let's go through an example. It says calculate the root mean square velocity of gaseous xenon atoms at 25 degrees C. Now this is the formula that we're going to use, so let's just write that out again. We know we have this, and it's the square root of all this, and then that on the bottom. Alright, so let's just see what we have. 3 times 8.314 joules per mole per Kelvin times 298 Kelvin. Notice the Kelvin here is on the bottom, this Kelvin here is on the top. And then all underneath that we have our molar mass, except it's in kilograms per mole. So we have to make sure that we can calculate that, because we've got to put it down here. Xenon, the first thing to understand about xenon is it's a noble gas, so it's not diatomic or anything, it exists by itself as one single atom, a monatomic gas. So when we talk about xenon, we know from the periodic table that 1 mole of xenon weighs 131.29 grams. But we have to have our molar mass here in kilograms per mole, not grams. So we've got to convert our grams into kilograms, just using this conversion factor here. So what we end up with is 0.13129 kilograms per mole. Alright, so our grams cancel out. So what we have on the bottom here is our 0.13129. You know what, I should do this in black, shouldn't I? Kilograms per mole. And of course I can't forget that I'm taking the square root of all this. Alright. Now, let me show you what we can do with our units here. Okay. Our Kelvin was on top here, and here it's on the bottom. Alright, we have moles on the bottom here, moles on the bottom there, so those will cancel out. And what we're left with is essentially units of joules per kilogram. Now, if we calculate all that out, what we get is, let's see, 237.93 joules per kilogram. Now we're looking for a velocity here, units of meters per second. Obviously, joules per kilogram looks nothing like meters per second. The fact is, 1 joule can be expressed in a different set of units. 1 joule is 1 kilogram per meter squared per second squared. So we can take all this and plug it into here. So what that says is we have 237.93 kilograms per meter squared per second squared, and we still have the kilograms that was on the bottom originally. So that's still there, and of course that means that those two sets of kilograms can cancel out. But not only that, we have squared and squared, those can cancel as well. So what we have is 237.93 meters per second. That is the root mean square velocity of gaseous xenon atoms. So really, the only thing that's going to make this different from one atom to another is this. and of course the temperature. Alright? So figuring this out is not all that complicated, you just got to know how to use this formula. That is root mean square velocity. Alright, thank you.